So here's an example related to an AC circuit, and we'll try to solve this using superposition theorem. And in this question it's asked to find I naught, that is in this branch. So I naught is given here, and if you observe the question, then there are in fact 4 sources. Three of them are independent sources, and one of them in this diamond shape is a dependent source, and the value of this dependent source is 2 I naught, and it's dependent on the current that passes through the branch where I naught is given. Now we have 3 independent sources, two of which are the voltage sources, and one is the current source. So as we learned that this circuit can be represented into sub circuits comprising of one source taken at one time. So since we have 3 independent sources and we are going to apply superposition theorem, and that is why we'll be drawing 3 sub circuits corresponding to the to each of the independent source. So one of which is this one. This is case 1. So here we have taken the first source, that is 3 angle 60 volts, and discarded the remaining 2 independent sources. And while we learned that in order to remove the other 2 sources, we will be replacing them by their internal resistance, and the internal resistance of a current source is infinite, that is it is replaced by an open circuit, and that of a voltage source is finite, or it's a 0. The internal resistance of a voltage source is 0, and thus it is short circuited. Case 2, we'll be having the second voltage source, and we'll be removing the other 2, this one and this one, so as shown in this figure. And the third case is we'll be taking the current source of 2 ampere, and we'll be removing the other 2 voltage sources, that is we'll be replacing these sources by their short circuits. And if you observe in each of these cases, so we are not going to remove the dependent source anyway. So if you have any independent source, and it was dictated when we learned superposition for DC, that if we have any dependent source within the circuit, it will not be removed. So be careful not to replace this dependent current source, this one, by open circuit. So if you are going to remove this and you are going to place an open circuit here, then the answer will be wrong. So we start with case 1. So we redraw the circuit. So we have a slide clipped from top, so it's again drawn here. So we have this diamond shaped dependent current source, the voltage source, and since we have this branch as open circuit, so it's as good as not having the branch. So we have removed the branch in this in this diagram. Now we assume that the current that flows through this branch is I naught dash, and thus the value of the dependent current source would be 2 I naught dash. So now we will be applying KVL to this loop, and we'll be avoiding loop that comprises of the current source. So we won't be applying the loop in the outer loop, the KVL in the outer loop. But before applying KVL to this smaller loop, if you're going to apply mesh analysis, which I think is the most easiest of all, or is the most convenient of all. So since in case of mesh analysis, it's better that you apply all the KCLs on the circuit itself. So suppose that you're given 2 I naught dash, the current that flows through this branch, then I naught dash is through this branch. Then in this node, if you apply KCL, then what you get is the current that goes from this node through this branch would be I naught dash plus 2 I naught dash, that is 3 I naught dash. So I have applied the KCL in this particular node, and now when I will be applying KVL in this particular branch, the loop 1. So before applying KVL, it's important to understand that since we are dealing with AC circuits, which means that for half cycle you'll be having this particular terminal as positive, and this as negative. For the next half cycle, this will become negative, while this will become positive. So which means that we have alternating or switching terminal, the switching polarities of these voltage source. So it's better that we try to apply KVL on instantaneous values, which means that for a particular time instant I assume that this is positive while this is negative, and the direction of current is coming from the positive side, whatever that current be, that is 3 I naught dash. And this 3 I naught dash, part of this 3 I naught dash goes through this branch I naught dash, and 2 times of the a part of this 3 I naught dash will pass through this branch. Now, since the direction of current you see is from left towards right in this branch, so we'll be taking this as positive and this as negative, this again as positive, this as negative, this as positive, this as negative. So there is an important thing to understand, that in case of DC circuits, it's the voltage source, the voltage terminal, that decides the direction of current. But in case of AC circuits, it's not necessary that the current will always be coming out from the positive terminal of the battery. It may be possible that the current may be going towards the positive terminal of the battery, which means that the direction of current would be reversed. This is only possible in case of AC circuit because of presence of inductance and capacitance. As I told you that inductance and capacitors, inductors and capacitor both have the property of storing energy and then giving the energy back. So that giving of energy back to the source is possible when the when the current flows against the positive terminal of the supply. So it may be possible that at particular moment or at any instant when I am analyzing the circuit, the current might be flowing towards the positive terminal of the battery. In that case, since I have assumed that the current, while writing KVL, I have assumed that the current comes out from positive terminal, and probably the current should have been entering the positive terminal, which means that if in this case, when I solve the circuit, I might get the solution or the answer for current as negative. So negative current means that whatever direction I have assumed in the circuit, and the answer that I am getting as negative means that the direction was assumed opposite to what it was actually flowing. So let us simply apply KVL to loop 1. It's very simple. So you assume that this is positive, and you assume that the direction of current is clockwise, so this becomes positive, this becomes negative, this positive, negative. So applying KVL gives you this relation. So we have voltage source, then drops, this is 2 I naught minus j3 I naught dash, then we have this as impedance as 6 ohms, j6 ohms, so this becomes minus j6 multiplied by the current that flows through it is 3 I naught dash equal to 0. And when we further solve this, so we are going to convert 3 angle 60 into rectangular coordinates using our calculators. So this is given here 1.59 plus 2.59j. So these are the rectangular coordinates of rectangular form of 3 angle 60. Then we solve this relation, we were left with minus I naught dash, inside braces we have 2 plus j3 plus j18, and what we get is 2 plus j21. So from this we get I naught dash as 1.59. so this is I naught dash equal to 1.59 plus 2.59 divided by 2 plus j21. Now we will be converting these forms again to polar form and then dividing it. So the final answer that we get for I naught dash is 0.144 angle minus 26.11 degrees amperes. So which means since we are getting this as in polar form, so one thing is that you will not need to worry much about the direction of the current that would be flowing inside the circuit as you used to do in case of DC network. So in case of DC network, it is important that the direction of current should be in accordance to the voltage terminals. In AC you don't need to worry about it because the current might be in accordance or it may be in the reverse direction or in opposite to the positive polarities of the voltage source. So if if the case is if the current is going to flow opposite to the polarities of voltage source, in that case you're going to get the answer with angles. For example, if you take voltage as 60 degree here, the voltage is flowing, if you consider the phasor of voltage with angle 60 degree, that of current is around minus 26 degrees. So you can say that the current lags more than so it's lagging around 90 degree, less than 90 degree. Now if we consider case 2, so let us consider this case. This is case 2. We redraw the figure again and simplify this figure. So we assume the current that flows through this branch is I naught double dash. So this becomes 2 I naught double dash, and this is open circuit, so we remove this branch, and what we are left with is this particular circuit, and we apply KVL to loop 1. So again, performing the same way of analysis that we did in our previous case, we are going to assume plus and minus momentarily here. Then we will be having, and the direction of current is given as clockwise, so this will become plus. So let me draw this again. So this is plus because current in 6J ohm goes from top to bottom. And again, if you analyze this circuit, so this is in fact the current that flows in the middle branch is from left towards right. So this is plus and this is minus. Again, this is plus, this is minus, and so on. So if suppose that we are going to apply KVL to this particular loop, so you can start from any point. So I start from the voltage source. So we have 2 angle 90 degree, the value of voltage source, and moving clockwise. So this is plus 2 angle 90 volts minus J6 into 3 I naught double dash, and again minus 2 into I naught double dash, then again minus J3 into I naught double dash equal to 0. Again, further simplifying this, we get 2 angle 90 degree. Notice that I have written here 3 I naught double dash. So this was obtained similar to the previous case by applying KCL to the figure itself. I didn't have to write current separately, that 2 I naught double dash is flowing in this branch and I naught double dash in this branch, and that is why the current that flows in this branch should be I naught double dash plus 2 I naught double dash. So you no need to write these. So this will be making your problem lengthier. So it's better that in short you write things on the circuit itself. It is possible. So I have applied KCL at this particular node within the figure itself. So I got this current as 3 I naught double dash. So solving the KVL equation further gives us I naught double dash as 2 angle 90 degree divided by 2 plus J21, and further simplifying by converting all the rectangular coordinates or rectangular forms into polar form. So what we get is I naught double dash as 0.27 angle minus 69.39 amperes. Likewise in the third case, we have this source of 2 ampere, and we short circuit the remaining 2 voltage sources, and what we are left with is this circuit. And now if we write the values of current, so I naught triple dash is the current that flows through this J3 ohm, which means that the value of the dependent source would be 2 I naught triple dash. And if you apply KCL at this node, so that the current that flows from this node towards J6 ohm would be I naught triple dash plus 2 I naught triple dash. This is 3 I naught triple dash. Now again, if I apply KCL at this particular node, so 3 I naught double triple dash is the current that goes into this node, and from this node 2 ampere goes upward, which means that the current that I am left with is 3 I naught triple dash minus 2 amperes. And again, this current, when it goes to this node, I again apply KCL at this node. So what I get is 2 I naught triple dash goes upside in this branch. It's 2 I naught triple dash. Then the current that I am left with that flows through this 2 ohm would be 3 I naught triple dash minus 2 I naught triple dash. and thus what I get is I naught triple dash minus 2. So the current that flows through this 2 ohm resistor is I naught triple dash minus 2. So let me erase all the stuff. Now if I apply KVL, so notice again that KVL will be applied to the loops that do not contain any current source. So if you look into the loop, if you look into this circuit, you will find that the smaller loops have current source of 2 ampere, and the outermost loop, the biggest loop, also have the dependent current source. So we will prefer applying KVL to the loop that comprises of this 2 ohm resistor, this inductor, this inductor. So this is the loop given by the direction of arrow. So applying KVL to this loop, we get, so we have I naught triple dash that flows through this inductor, and you take this as plus and minus. Again for J6 you have plus above, minus below. For 2 ohm, plus at the left side, minus at the right side. So this is minus J3 I naught triple dash minus J6 3 I naught triple dash minus 2 into I naught triple dash minus 2 equal to 0. If we further solve this, you get I naught triple dash equal to 2.64 plus J 0.14 amperes. Now we will be applying superposition theorem, since we obtained the value from the 3 sub circuits, I naught dash, I naught double dash, and I naught triple dash. And using superposition principle, we say is that the current that will be flowing through the branch when all the sources are connected is the sum of the, so in case of AC network it would become Phasor sum, in case of DC network it was algebraic sum. So now we will be taking the Phasor sum of all the currents that we obtain from the sub circuits, and thus by superposition theorem what we get is I naught equal to I naught dash plus I naught double dash plus I naught triple dash, and the answer is 2.86 minus J 0.77 amperes. Now I request you all, so this is the complete solution of the circuit using superposition theorem. This is case 1, then I have written case 2 here and case 3 here. Then by superposition I get the answer as 2.86 minus J 0.77 amperes. Now I leave the problem for Thevenin's and Norton's upon you, and anyone who first solves this question and verifies the answer, so you'll have to mail me the solution using Thevenin's theorem and Norton's theorem. So the first one who solves this question using Thevenin's and Norton's correctly, he will get additional bonus marks. So you'll have to mail the solution at this particular email ID.